Okay, let's talk about trig functions, okay? Here's our first trig function we're going to look at. F of x is equal to sine of x. Actually, you know what? I'm going to use f of x. I'm going to use y. Why? You'll see why in a minute. So, we have y equals to sine of x. And we know what that looks like. We're hopefully pretty good at drawing these now. But what we want to look at today is the rules to differentiation. And we've kind of looked at rules for what kind of functions? Like normal functions, like parabolas, x squared, x cubed, any powers, right? What did we look at yesterday? We looked at
gradients.
Exponentials. We looked at, well, the derivative is the gradient function, right? What other functions did we look at? Logs, right? We looked at logs. And now, my projector's a bit funny, but that's okay. We are going to be looking at trig functions. So, here, right, I said there's some intuition we can look at when we're looking at these gradients, right? Because if we make these a bit more, how should we make this scale? So I said this is our trig graph, right? And if we zoom in at this point, what does the gradient look like at this kind of point here?
1 on 1.
It looks like 1. On 1, or a gradient would be 1. At these horizontal points, it's a 0, right? Because it's a flat, it's a horizontal. Okay, let's keep going. What about now at this point here? What does that look like? Looks like a negative 1, right? If you zoom in close enough, it looks like a straight line whose gradient is 1. Yeah, so let's get back out of here. And then, let's have a think about what the gradient might look like. If we're trying to graph the gradient function, right? Because remember, the problem with functions is that the gradient's always changing, okay? So, let's think about, okay, at this point, we theorize that the gradient is 1. And at this point, what do you reckon the gradient was? It was 0. And in fact, let me put the scale back to the pi so we can see what we're dealing with here. Pi on 2, let's do. There we go. Alright. What did we say over here? It looks like, what did we say the gradient looks like over here? Negative 1. What about here? Going back to 0? Yep. And here we'd be going back to, well, it's 2 pi over here. Well, in terms of a gradient, it looks pretty much the same as back what we had over here. It looks like it would connect back up with this guy. Laura was thinking, yeah, it looks like 1. That looks kind of interesting. What does that kind of look like to you?
It's going to be this one.
Like an absolute. So here's the thing, right? The gradient, when the gradient changes, is the gradient just going to be, the way it's changing, is it going to be linear?
It's just another way.
It might be. Is it just another wave? Here's the hypothesis, right? Let's have a look. So here's our derivative.
Maybe it is.
Oh. Wait, what was that? What's this? That's a cos graph, right? So our theory is that if I took the derivative of sine of x, it looks like we get cos of x, right? So y dash could be cos of x, yeah. So like I said, oh, what? Is this surprising? No, but I saw this cos graph, like derivative, right? So they yield some surprising results. We take the derivative of one trig function, we get another trig function, right? That's kind of interesting, okay. What if we, now I don't know if we've looked at this, but we can think about this now in 2 ways, right? Well, let's say I took, yeah, so let's first think about if I took y equals to cos of x, right? As my original function. So let's put this, let's get rid of this derivative one now. Okay, so here's our, wait, what if tan just comes into it? Well, let's find out. So here's our cos graph. Let's think about gradients. What's the gradient at this point now? 0? So maybe it's a sine curve. I don't know. Let's find out. What's going to be here?
1. Negative 1.
Oh, hang on. Harry called you out. All right, negative 1 over here.
That's what I meant.
Yeah. That's what they all say.
Wait, so is it just negative?
All right, what about over here? What's happening over here? What's happening? Work with me, people. What's happening? 0. Thank you, Laura. 1.
0.
And 0. Laura to save the day. Let's have a look what this looks like. Here's our derivative graph. Bada bing, bada boom.
You're a sin.
So, that means the derivative of our cos graph is not just a sine, but it's been reflected in the x-axis. So we're working with negative sign. But here's the thing, right? Like, if you look at this guy,
So they say negative one.
you can see that these cos and sine graph derivatives are very closely related, right? So if you take the derivative enough times, what do you think is going to happen? Kind of, it looks like it'll.
Is it like complex numbers?
Maybe like if you took the derivative, this is the second derivative, right? I don't know if we've talked about that, but you can just take the derivative again. There's no reason why you can't, right? So that'd be negative sine x. Now, apply your kind of normal ideas. If you took the derivative of negative sine x, what would you expect to get with your derivative rules? Well, the negative is just a constant there, isn't it?
So negative cos.
Negative cos x.
Do we go back to
And then negative cos x, well,
Sine.
if we take the derivative, because if you think about the y equals to cos of x, if that derivative is negative sine of x, if you had negative cos of x,
Literally like complex numbers. Oh, because it's the unit circle.
alright, negative cos of x, yeah, that would just be positive sine of x, which looks like we loop back to where we begin with, right? So we've got this interesting little pattern going on here where the derivatives kind of cycle through, sorry?
If you did 5 dashes, you just put a line through.
Is it like a Roman numerals tally? Not Roman numerals. Like a tally, the fifth derivative, right? Usually they will actually do something like this, I think. Yeah, just to, yeah. We don't really look at like more than 4. Like I don't think we even look at really more than 3 in this course anyway. But that's an interesting thing, because with your usual curves, right? When you take derivatives, at a certain point they just become straight lines, right? Because they're like linear, or they just go away, they become nothing. But these ones, you can take these derivatives infinitely, and they'll just like keep looping around, which is really, really cool. But that's only for 2. Okay, let's write these down, let's generalize these. The interesting thing to also note is that with your trig functions, they're actually functions. They're kind of special in that sense, right? So if I have y equals to sine, now we don't just have to have x, we can have any function inside here, okay? This is actually a function inside a function, right? So anytime we had that, like think back to your powers, right? You had something inside brackets and you had a power there. We had to do something with that. Similarly with sine, we have to sort of treat it like that, a function within inside a function. So our derivative, y dash, is going to be whatever is inside the brackets there, f dash of x. We take the derivative of that, sine of f of x. Okay? So that's our first derivative rule. So just as an example, right, if I had y is equal to sine of 7x, I can do that in a moment, yeah. If I want to take the derivative of this, right, I'd say, okay, well there's a 7x inside my brackets. We take the derivative of that. What's the derivative of 7x, Harry? 7? We put that at the outside as a kind of coefficient, and we keep the original. Oh no, we don't keep the original the same. Oh, what did I just write here? Why did I write sine of x? Just testing you guys here. Sorry. Say that again. So if I take y equals to sine f of x, my derivative should be cos of x. Don't know why I just wrote sine of x again. Sorry about that. My mistake.
So is it 7 cos 7x?
That's right. Sorry, 7 cos 7x.
Beautiful.
But let's just look at a couple more examples first here. Y equals to cos of f of x, right? So now looking at what we observed over here, if I want to take the derivative, same idea, right? We're kind of applying a chain rule situation here because we've got a function inside a function, because cos is a function, f of x is a function. So if I take the derivative, f dash of x, that is brought out as a kind of constant. Oh, sorry, I shouldn't say constant. It might not be a constant. As a coefficient. And then, yeah, we actually have a negative in front here. Sine f of x. So these are our 2 derivative rules. You got those down for me. And we can do an example for cos as well. Yeah.
When are we going to use this in real life?
So the interesting with cos and like trig functions, right? Like in your assignment, it's actually about talking about real life applications, right? So the first one is looking at what kind of waves? Do you remember in your assignment? One of them is looking at, I remember, yeah, sound waves, or any kind of really waves in physics are represented by some variation of a trigonometric wave. The second one is like tidal waves you're going to be looking at. So like the rising and falling of a tide, like that's cyclical. It's periodic, right? Which is exactly how a trip wave is. And the really cool thing is commercial trends, right? So when you look up keywords in Google, right, sometimes they have spikes in their periods of time, right? Like think of an sorry? Yeah, well, have a think, like, what kind of things would be more popular during certain periods, right? Think about it. Like, if it's a seasonal thing, like if you're talking about jackets. Well, jackets, I feel like that's kind of an all-year-round thing, would you? No? You only wear jackets in certain seasons. What's something that could be seasonal?
Winter again.
What's something that's kind of seasonal? Sorry? What?
Christmas
Weather, right? So let's think about ski season. Right, when are you going to be looking for skis? Probably during winter, right? Or just before winter. Or if you're or we can be more specific. But yeah, water skis. Let's see. I want to Google snow skis rental, right? So probably only looking for snow skis rental during the winter period. That's just an example, right? So these kind of trends can be modeled using these trigonometric functions. Yeah. Oh, glad you asked. Great question. This one over here, though. All right, we want to be thinking, okay, just being careful, because when you take the derivative of cos, we get negative sign, and that applies to when we look at these kind of questions. So I look at what I've got inside here, I take the derivative of that. Kyle, can you help me out? Derivative of what I've got inside these brackets? Just 3, yeah. So I've got the derivative is negative, remember, don't forget the negative, negative 3 sine of 3x plus 4. So what's staying the same is the function inside the brackets there. Okay.